Hello everyone, welcome back to the class. And this is the fifth lecture of the chapter we were studying. It is electric charges and fields, the first chapter of your second PUC, and which is the chapter which carries the maximum weightage of marks, and it is total of 11 marks you will be getting. So before going to the further concepts, let us have a small recap of what all we studied in the last class. Now if I consider, it was we studied that is the electric field. So we had to calculate or derive an equation for the electric field due to a dipole at what point? At equatorial point. So equatorial point in the sense, if this is your dipole, at the center, the perpendicular distance is something called as equatorial point. So at that point we calculated or we derived the equation of what it is your electric field. So this is what we studied, and we took individual charges and individual charges electric field we considered. So and if I consider the total electric field, so as this is in your equatorial point, this electric field produced by the two charges is split up into two components according to your trigonometry. It is sine theta and it is cos theta. So this is what I had told you. I had explained this pictorial representation very cleanly in the previous video. Please go back to the video and check with it. So if I consider the sine theta over here, so electric field, two electric fields, the sine theta components you can find, which is at their opposite distance, and opposite distance, opposite direction, it would cancel each other. So if I consider the directions which are along one side, so that is your cos theta is the component which gives you the total electric field. So the two components are onto one direction, so e cos theta plus e 2 cos theta tells you about the total electric field of a dipole at the equatorial point. So this is what we studied. We took cos theta also into consideration, and how is it? So total electric field tells you about E Q, and what is this? Positive Q cos theta plus electric fields of minus charge cos theta. So you're adding both the components, okay, of both the charges and both the electric fields. So after you added cos theta, you're going to take it as common. So what is the formula for EQ? So electric field, it is 1 divided by 4 pi epsilon naught q divided by the distance. So what is the distance? According to the Pythagoras theorem, you have got, if I take this triangle, the two sides you're going to add and square it, and root of it is something called as your hypotenuse. So you have got r square plus a square. Actually root I had to take, but I'm taking the power, not root, but as 1 by 2, half. It is one and the same. Root and half are equal, so that's why I have taken r square plus a square to the power of half I have taken. So now if I consider, as I have taken from this equation cos to be as common, you have got two electric fields, so that is why I have written 2 over here, twice of the electric fields. Okay, electric field formula. So if you check with this triangle also, the value would be same, because the distance is a and the distance of this one is r, and the hypotenuse value would be the same of this, that is r square plus a square to the power of half. So if I consider actual formula of this one is r square, so distance square, is it? So what do I get in the power of the denominator, that is your distance? So r square to the power r square to the power of half you're getting. So half into 2, 2 gets cancelled, and the power what you get is r square plus a square you're getting. So now if I consider the cos theta, the calculation is in this way, taking the triangle. So what is cos theta according to your trigonometric function? It is your adjacent by hypotenuse. So if I consider this to be as adjacent, this is your hypotenuse, and I have written and substituted in this value. So after all the calculations, finally you would get the value, that is E is equals to P divided by 4 pi epsilon naught R cube you would get. So how do you get this P? With the formula of dipole. So this is what we studied in the last class, and also we studied with another concept, that is something called as dipole in the uniform electric field. So uniform electric field, you will be having another concept which the dipole experiences, that is something called as torque. It is a some sort of force, a rotatory force you call it. As you have studied in your first PUC, the concept of torque is taught still more in depth. So if I consider this is your electric field, when I keep a dipole, that is your positive charge and your negative charge, so these two experiences certain forces. That force is something called as torque. It is a rotating force. So if I consider the formula, force torque is equals to force into arm of a couple. So instead of arm of a couple, for your better understanding, you can write it is a perpendicular distance between the forces. Okay, so now substituting the values for the torque, F means it is force. Okay, force. So what kind of force is acting on it? It is F is equals to Q into E. So how do you get this formula? From your electric field concept. So now taking the arm of a couple, which is your perpendicular distance between the two forces. So if this two are the forces, the perpendicular distance, so the distance is 2a sine theta. So you substitute. So how do you get this P in your next equation? It is by your formula of dipole. So finally you got what is your torque. So this was the thing we studied in the previous classes. So now going to the further concept, that is something called as continuous charge distribution. See children, if I consider continuous charge distribution, before going to this concept, I would like to tell you, I was dealing with all the minute particles. So firstly, I took an atom. In an atom, you have got proton, neutron, electron, yes. So if I consider electron, it is negatively charged, proton, it is positively charged. And if I consider, according to the concepts of electrification, adding or removing of an electron tells you the charge of an object, I had told you. So we were always dealing with atom, electron, proton, so minute particles. Now if I consider the macro particles, that is your visible to your eyes. So say for example, taking 1, 2, 3 dimensional objects, like say if I consider the first picture, okay, the first picture tells you it is a rod. It has got a length, so it is one dimension. Now if I consider it has got a length into breadth, so two dimensional, it has got a area in it. Okay, so now the third figure, if you see, I can say that it is three dimensional, it has got volume inside it. So if I consider a box has got some volume in it. Okay, so it is a three dimensional. So if I consider the continuous charge distribution, if I consider a rod, if this rod is charged with some charges, positively charged, so it has got continuous charge distribution on it. Now if I consider this figure B, if this is charged positively or negatively, there is a continuous charge distribution. So now if I consider this continuous charge distribution, it tells you about a very large object has got many atoms in it, and these atoms have got charges in it. So how is this? You're going to calculate the formula of a bigger object you're going to study in this concept. Now going to the formulas. So if I consider the first one, for line charge distribution, so actually it is linear charge distribution. Okay, so typing errors are there, please forgive me. So now if I consider the linear charge distribution, linear, which tells you it is a line, a straight wire or a rod or something which is one dimensional. So if I consider for linear charge distribution, charge element is small length. So one thing you should understand in this concept, delta L means I'm not considering the whole thing, but as can you see the red mark over here? It is a small length you're considering. So during your calculation, you would just write it as a delta L. So you can find your delta L. On this delta L, you have got delta Q. So on a small length, you have got small number of charges. So in the same way, if I consider linear charge distribution, so it tells you lambda is equals to Q delta Q divided by delta L. So you're understanding, if I consider a small length of the rod, that small length has got small amount of charges. So this is something called as linear charge distribution. So next for the, so again there is a mistake, and surface charge distribution, it is called as surface. So here if I come back to this one, it is one dimensional. So what is the unit of Q? It is C, coulomb. And if I have the length, it is measured in meters. So coulomb per meter, or else you take this meter to your numerator, coulomb meter inverse you would get. So next, going to surface charge density. So there is, if I consider a small distance, so small area of the surface, so I would consider the formula. So this one is represented by sigma. So if I come back to this, lambda is equals to delta Q divided by delta L. So now if I consider the surface charge density or surface charge distribution, so this is called as sigma is equals to delta Q divided by delta S. So small surface area, small charges is being distributed. Okay, so this is something called as surface charge density, and its unit is, so surface, I'm talking about certain area, and it is two dimensional. And if I consider the unit of it, Q is coulomb divided by meter square, it is two dimensional, so square you would get over here. Next, going to another concept, it is a volume charge distribution. So volume you have got in that. So if I consider a rectangular box, so your geometry box, your lunch box, like that, so it is represented by rho is equals to small charge in small volume. So delta you have got, and the unit of it is a C, that is coulomb divided by meter cube. So this is all about your concepts of continuous charge distribution. In this, there is no derivation. You have to know what is the formula of this. And then going to the next concept, that is okay, before going to the next concept, let me tell you how to substitute certain values. So as I have told you, given the values of your linear charge distribution, surface charge distribution, and volume charge distribution, remember all those formulas, and you would ask to substitute that value in another formula. Say for example, if you have got electric field due to a volume distribution of charge you have got, so they are telling you in a electric field, okay, electric field due to a volume distribution. So if I consider this is your volume, there are many atoms in it, billions millions of atoms, and on those atoms you have got certain charges. So those charges produces electric field. So that they are telling you in a volume distribution what is the electric field value. So what is it? So in a volume charge distribution, what is the electric field? So electric field due to a volume distribution of charge. So what you're going to do, take the formula of electric field E, which is equal to 1 divided by 4 pi epsilon naught. Actual formula was Q divided by R square. So what is Q? So if I go back to this formula, you have got rho is equals to Q divided by V. So cross multiply rho into delta V goes on to your left hand side, and what is that? You would get Q. So rho into delta V. So I can say that rho into delta V you got. So E is equals to 1 divided by 4 pi epsilon naught rho delta V divided by R square. So you can find it is a small volume I have taken delta V. Now to exaggerate it, to make it more and more for the whole volume, so you can say here, see here, that is for small volume element delta V. So if I consider the whole volume, the entire volume, you're going to write it as summation. So you're summing up all the delta V value. So delta V, delta V, delta V, delta V. So you're going to add all the delta V's of the whole object and you're getting the total electric field of the entire volume whichever you take. So this is how you're going to substitute certain values to get the value of electric fields. Hope I have made it very clear to you. Next, going to another concept, that is your Gauss law. So what does Gauss law tell you? So now if I consider this sphere, Gauss law tell you to consider a spherical imaginary surface of radius r. So consider a spherical imaginary surface of radius r enclosing charge q. So if I consider this is the imaginary line, so it doesn't have any sorts of matter over there. Okay, so it has got an imaginary line where inside that there is a charge, and from the imaginary line to the charge the radiuses are. So why are they asking you to consider a certain spherical imaginary surface? Because to find the charges within that surface. So now if I consider in this whole universe, you have got many atoms and molecules. Okay, so if I go finding out what are the number of charges, can I go to the entire world and check with what is the number of charges? No, and that is why they have given you certain imaginary surfaces. Within that you have to just consider what are the number of charges. Just for our convenience, people have done this law. So this is something called as Gauss law, and they are telling you delta S be small area of the surface of the sphere. So this would be the surface, small surface area of the sphere. So by assuming to divide whole into many small areas. Okay, so Gauss law tell you to consider imaginary surface and the charges within that. So now if I consider there are, so just imagine there are 10 charges within this and 2 charges outside the surface. Now they would ask you what is the net charge of it. So you would be writing only 10 coulomb of charges are there according to Gauss law. So what does Gauss law tells you? Within the imaginary surface you have to find the total number of charge, but not outside where I had told you 2 coulomb of charge is there. No, you're not supposed to calculate that, but you have to calculate within the surface of the imaginary surface, whatever it is according to the Gauss law. So this is all about your Gauss law, and there is a statement also for that. Before going to the statement of the Gauss law, let us derive some derivation which tells you about the exact formula of electric flux. Okay, now if I consider the electric flux which we calculated earlier, that was phi is equals to E into ds. So what was the thing we studied according to the electric flux? It is if I consider surface, a metal plate, so through that plate there are many electric fields passing through it. So that is something called as electric flux, I had told you. Yes, if I consider one surface, through that electric field is moving, and through this surface the electric fields are moving, and that is something called as electric flux, I told you. Yes, so I had given you 2 cases also why cos theta you would get, isn't it? So now if I consider this formula, again phi is equals to electric field through certain area of the metal plate, so E into ds, small surface area. So now if I consider this formula, so substitute the value of electric field here in this So what is that? You would get 1 divided by 4 pi epsilon naught q divided by r square is your formula for electric field. So this small r cap tells you about the direction of what? Electric fields, and it is delta. Yes, you would get. Okay, now after this, taking out direction vector r, so you would get the formula to be as phi is equals to 1 divided by 4 pi epsilon naught q r square delta. Yes, you're getting. Let me not take any of the vector forms here. No direction, nothing, just a magnitude we shall consider. Now we're taking the same thing as it is delta. Yes, let me put summation symbol here. Why do I put summation symbol? So if I consider small area of the sphere, I have taken delta s. ds and delta s are same, children, so it tells you about small surface area. So okay, so now if I consider small delta s, adding all the small surface areas, so you are summing up, summation, so you can find something like this. It is summation symbol in mathematics. You're summing up all the small areas of the sphere. So as you sum up, what is the surface area of a sphere? Sphere is your three-dimensional, and what is the surface area of a sphere? It is 4 pi r square. Substitute this value over here. So what do you get finally? Phi is equals to 1 divided by 4 pi epsilon naught q divided by r square, and if I consider this sigma delta, yes, summing up of all and the entire sphere's area of the surface area of the sphere, you would get 4 pi r square. Just substitute. So here what are the things going to be cancelled? It is 4 pi r square, 4 pi r square. The remaining thing is q divided by epsilon naught. So this is another formula which tells you about the electric flux. So total electric flux through a closed surface is equal to 1 divided by epsilon naught. So what is this epsilon naught? Absolute permittivity. So if I according to free space, so if I have got in a free space, so say vacuum or air medium, for that the epsilon naught value would be same. If I consider different mediums like water, any other mediums, okay, so then there will not be any epsilon naught. Rather, if I consider any other mediums like water or anything else, then you would consider not to be as epsilon naught but epsilon r. So not, except not, you're going to write it as r for any other mediums. So why do I tell this? If any of the numerical problems are given, and if they consider any other mediums, and for that medium they would give a constant value, that is epsilon r, so you have to write that. So instead of epsilon not, epsilon r you're going to write. So the charges within the any of the medium, it depends upon that. That's it. So now this is all about your electric flux, Gauss law, according to your Gauss law. And implication of this law is that when there is no charge enclosed in a closed surface, total electric flux through it is zero. So what do you mean by this one? So if I consider one imaginary surface, if there is no any charges within that, then it tells you that there is no electric flux. So total electric flux is zero, they are telling you. So easy it is. Is this clear? So next, going to another concept, and that is application of Gauss law. So how Gauss law is applied according to linear charge distribution. So what is the formula of linear charge distribution? Lambda is equals to q divided by L. So now according to that, we are going to calculate using Gauss law what would be the total electric field. Okay, now how is it? Taking the pictorial representation, if I have got infinite length of a wire or a rod, which it is positively charged, so you can find positive charges on it. So now according to the Gauss law, application of Gauss law, is it? So now if I consider one Gaussian surface, that is your imaginary surface, so within that surface you're going to calculate what? Electric fields. So you're going to consider two formulas, that is your Gauss law's formula. So phi is equals to E into surface area. Yes, so that is one formula you'll calculate. Then linear charge distribution formula you will calculate, and also you'll be calculating using another formula, that is your Gauss law formula. Phi is equals to Q divided by epsilon naught. These three formulas you'll be using. And what is the thing in physics is you're putting one formula into another formula and creating new formula. So it is very easy. Just what you have to do is hardly 10 to 13 formulas you would find in this chapter. You have to remember those formulas, that's it, and you should have a technique of how to use it. So then you would succeed in your examination, you will understand the concepts, so you will get good marks also. So I would always ask you to concentrate, learn the concepts, not just for your getting marks, but also to gain knowledge. So now going to the further derivation of this one, let me take phi is equals to E into surface area. So now what is that I'm telling you? If I consider this rod has got some charges in it. So now this produces electric fields on both the sides. If I consider, so this side electric field is produced, this side electric field is produced. So its length is L, and there is a Gaussian surface. Now if I consider 2 pi r L, so what is this 2 pi r L? According to the electric flux, it tells you that the charge produces electric fields. So can you find this E arrow mark? So which is perpendicular to certain distances. So if I consider the area of the cylinder, except this two ends of it, so why do not I take the ends of the cylinder? Because I have mentioned it is infinite. So just for your my convenience, for you to understand, I have given the other two sides. But if I take the entire thing to be as infinite, you would not find these two sides, only rather this block. So this thing you would find the cylinder except the top and the bottom. So the surface area of the cylinder, I would consider it to be as 2 pi r L. So what is this? The distance of this cylinder, so the length of this cylinder. So what is the formula now? Substituting the value of surface area of curved surface area of curved surface, you would write it as the area of the cylinder except this two sides, that is 2 pi RL. So you got one formula for your electric flux. Now taking, but charge enclosed in Gaussian surface. So what are the charges enclosed in the Gaussian surface? You have got Q is equals to lambda into L. So how is this formula? According to the continuous charge distribution. So if I consider one dimensional, it is your linear charge distribution of this rod. And what is the formula? You have got lambda is equals to Q by L. So if I cross multiply, you would get Q is equals to lambda into L. So by Gauss law, you have got Gauss law. Why Gauss law? So this rod, so this rod is being enclosed with a Gaussian surface. Within this you have to find what is the electric field. So I have taken the formula phi is equals to Q divided by epsilon naught. So if I consider this phi, so already I have substituted and calculated what is the value of phi. It is E into 2 pi r L. So what is the formula I have got? E into 2 pi RL. So substituting the value, you would get E 2 pi RL again is equals to. So you are substituting not only that, What is the value of q here? You have substituted it as lambda L divided by epsilon naught. So what was the aim of this derivation? It was to find the electric field within the Gaussian surface according to your Gauss law, and that is why I have just kept E aside onto your left hand side and taken everything onto your right hand side of the denominator. You just take it to your denominator, so L gets cancelled already, and final value you would get 1 divided by 2 pi epsilon naught lambda divided by r. So this is all about for our today's class. We studied how what is a Gauss law and what are the applications of it. Not only that, in the next slide if I go, you'll be finding how, again, the application of Gauss law, but with two-dimensional object, that is your finite plane sheet. So using this you would calculate how calculate what electric field according to your Gauss law. So let us study this in our next class. I hope I have made you very clear with the concepts, and if you have liked the video, understood the concept, please do like, subscribe and share it. Thank you.